Hey there, my name is Alejandro, and welcome back for day 124 of me doing the Daily LeetCode challenge until I reach 1 year's worth of free contributions here on GitHub. So today's problem is for November 17, 2024, and let's get straight into it. Okay, today we get LeetCode hard problem 862, shortest subarray with sum at least k. Given an integer array nums and an integer k, return the length of the shortest non-empty subarray of nums with a sum of at least k. If there is no such subarray, return -1. A subarray is a contiguous part of an array. Okay, let's look at an example. So nums here is equal to 1, k is equal to 1. Output is, okay, so they're not just going to explain. Okay, return the length of the shortest subarray that has sum at least k. Okay, so here k is equal to 1, so you can just have one element here, just the 1 here. So yeah, 1. K is equal to, okay, so, or -1 if no such subarray. Okay, okay. So 1 plus 2, yeah, the sum of the entire array is less than k. So okay, so if sum of nums is less than k, then straight up we just return -1. All right. Otherwise, there is an array where it is possible. Although, can numbers be negative? Oh, okay, numbers can be negative. Okay, so it's not this simple. It's not that simple. It's not that simple. Okay, so here numbers can be negative. Nums is equal to 2, -1, 2. K is equal to 3. Yeah, output 3 is like all the numbers all together. Okay, so you might have to do. Okay, so this is interesting, right? Because there's problems like, you know, get subarray with maximum sum, right? And the point is that like you start from the beginning and you like grow almost like a sliding window technique until you get to, you know, like a negative solution. And once you're at a negative solution, you might as well ignore that and start back at 0, right? And start like only including elements from then onwards, right? I wonder if there's such a similar idea in a problem like this. So like, first of all, I see the word shortest. So worst case, that means we can like, you know, rely on something like greedy, divide and conquer, or DP, but most likely something like dynamic programming, right? So we can usually almost always rely on something like dynamic programming. The only problem is that like for these type of problems where it's like subarrays and not subsequence, it's not as easy, right? Plus, if this was subsequence, then you could just, you know, take the max number in nums every single time, right? So it's like, you know, you could sort nums and like, you know, take the biggest number and keep taking the biggest number over and over until you get, you know, a sum that is at least k, and then that would be your shortest solution, right? But here it's not subsequence; it is specifically a subarray. I wonder, maybe it is an idea, like, you know, get subarray with sum at least k, or with greatest possible sum, and it's like every single time you see something that's greater or equal to k, record the length of that. Or, you know, we can start from like the beginning of nums, keep adding stuff until we reach a size k solution. But the point is that nums is not sorted, right? So right. Also, yeah, if we do a DP solution, right, we could solve this problem up to like a certain index I, right? So like, yeah, okay, if we do this, also, yeah, what are the constraints as well? Okay, 10 to the 5, so we need to do a linear or n log n solution, right? If I do this in terms of DP, right, so if I know the solution up to the ith index, if I know, you know, best solution up to index I minus 1, can I find best solution for up to index I, right? So case 1 would be same as best solution up to index I minus 1, or case 2, say solution. Okay, suppose solution to index I minus 1 is equal to k prime, or is equal to n, right? Case 1, so n. So here we'll say up to. The only problem, right, is that this might end up being an n squared solution if I do O of n cases with each O of n work inside of them, right? That starts being a little annoying, unless I use the results to solve each one, right? or no, or okay, or no. What I can do is just like, instead of best solution up to index I minus 1, I can say solution that ends at index I minus 1, right? It starts to get a little tricky. Like I'd have to store like, the indices where each solution started from, and I kind of iterate over that thing onwards and bigger, almost like a sliding window. Right. I'd have to know where the indices started, right? So that when I add index I, it's like I'm introducing a newer, larger number, or even a negative number, right? Okay, but let's not think about negative right now. If I add a newer, larger number, that's like I gotta start taking away elements from the left, right? If I add a negative number, I gotta start adding elements to the left. But then in that case, I might as well take the solution that ends at the previous one. Okay. I mean, this is a LeetCode hard after all. This is a LeetCode hard. Okay. Okay. Right. And k is equal to, okay. So we want the shortest subarray, right? Shortest subarray with sum at least k. So it's like, yeah, no, okay, I do like a DP-like idea. It's just that it's going to be an n squared solution, what I'm thinking of, right? We got to figure out how to do the work inside of the DP body efficiently, right? Where it's like we can do some best solution up to an index I, right? And then it's like what we return is the best solution up to the last index here. When I do that, how do I use the previous result to essentially help me arrive at my solution, right? If I know the result up to index I, okay. So self.memo of index I will give me some left and right index, right? Let's just say for the best solution. This is the shortest. So this is the indices that make up, the shortest non-empty subarray. And can k be 0? K cannot be 0. Okay. I mean, worst case is like we do a total of O of n more work instead of the DP calls, right? Where it's like, yeah, I keep incrementing this left pointer, but I never go backwards. Maybe one thing I need to do is also like compute prefix sums. So it's like, between two integers, two indices, I need to know like efficiently, like really quickly, what is their difference in sum, right? So it's like, if I'm at a current index j and I want to know like, okay, this was my previous r, like if I take all the elements between r and j, right, what is like that sum and so on, and you'd be able to do that efficiently. So maybe one of the things I should do is build like a prefix sums array, right? So like here we'll do prefix sums to nums of 0. Right, nums, okay. Or for num and nums, prefix sums, yeah, for I in range 1 all the way up to the length of nums. And here we'll start with nums of 0. Here we'll do dot append prefix sums of -1 plus nums of I. There we go. So here we can do print prefix sums, and here return what? So here we'll return a 0 for now, right? So let's make sure that we get things wrong. And so for these cases, it might not be the most useful, right? But if we look at something like case 3, it's like, yeah, so here the sum up to this index is 2, the sum up to this index inclusive is 1, right? And the sum up to this index inclusive is 3, right? Ooh. Wait, okay, maybe this is the key to this problem as well. Because here we're dealing with sums of at least k. Okay. So I can easily, like, right, if I want, you know, prefix sums of I is equal to sum of nums from 0 up to I, right? Which implies that sum of nums from I to j equals prefix sums of j minus prefix sums of what? I plus 1? Or wait. So I want from I to j, right? So maybe I do I minus 1, yeah. Yeah. Yeah, and if I is equal to 0, I just make this 0. I is equal to 1, then I want to ignore, yeah. Minus if I greater than 0, else 0. Right, so something like that. Okay, we can do self.prefix sums is equal to prefix sums. Here we'll do definite. Actually, here is like get subarray sum between self, I, and j, right? Here we'll say return self.prefix sums. So here we'll put in there, right? Self.prefix sums of j minus literally this, right? Or we can make this even easier. So if I is equal to 0, return prefix sums of j. Otherwise, here we'll return self.prefix sum Here we'll just do assert I is greater or equal to 0 and j is greater or equal to 0. Here 0 less than or equal to I less than length. Okay, this is fine. Self.prefix sums of j minus self.prefix sums of I minus 1. Okay, so now we have a get sum of nums from I to j, i.e. including index I and index j. Okay. So we can test this also against, like, a big array. Right, but like for something like this, if I want, like, the sum from here to here, right? So this would be j equals 2 and I equals 1, right? So it should be just 1, right? And so here if I do print self dot get subarray sum length of num nums minus 1 minus 2 length of nums minus 1 if nums is equal to 2 negative 1 2. There we go. Let's just make things easy. Here we'll, okay, let's make our life even easier. Let's just say index 1 and index 2. Yep, that makes sense. And so this is example 3. So yeah, so here we get 1 as expected. Okay. So now we're able, given an I and a j, we're able to figure out the sum of that thing, right? And an O of 1 time. Get subarray sum I comma j is now a function that returns the sum between indices I and j in only O of 1 time. Exclamation point, exclamation point, exclamation point. Okay. So now we have that set up, right? We spent O of n time. So this is all O of n, building our prefix sums, and now we have a function that is able to get us the subarray sum between an index I and j in O of 1 time. So that's going to be very powerful here in this problem, where you need to find the shortest subarray with sum at least k, right? So essentially it's like you need to find an optimal I and j. Now the only problem, right, is that we're only allowed to go up to a linear solution, right? So it's like how are you going to do this? How are you going to manipulate 2 pointers and do this in O of n time, right? Which means that either it's going to be like some 2-pointer idea, where it's like, you know, you have them on the left and right and increment one, decrement the other, blah, 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 and have them meet at some point, or you're going to do like some sort of sliding window technology. Because the only thing is like, yeah, this will be very, very easy to do with DP. But again, with DP, the only things that are coming to mind is either a solution which requires me using I and j pointers, which obviously is just not going to work because it's going to be too slow, or I have, you know, only a certain index, so it'll be 1D DP, but the work inside of it might be linear time. Okay, but that one looks more promising. So maybe we give it a shot. So here, if we do def dp, we'll do self, and here we'll also say, hey, self.nums, self.k is equal to nums and k. And here we'll say, hey, assert 0 less than or equal to I less than length of self.nums. Assert 0 less than or equal to j less than length of self.nums. There we go. Okay. Yeah, so this will take, we won't need the nums and a k, we'll just need an index I, right? So here we'll say self.memo is equal to a empty hash map. Okay, so here, yeah, if I in self.memo, turn self.memo of I, otherwise, yeah, self.memo of I is equal to res, return res, and then res is some sort of, you know, like float of infinity kind of thing. There you go, bada bing, bada boom. Okay. So it's like here, it's like we could do this 2 ways, right? Either I do the, I could also, could I binary search my way through this? Okay, I have 2 ways to essentially force this DP with an index I. Either I do, hey, either it's like you return to me the best possible answer up to this index I, but you're not forced to end at index I, right? And that way, when I do DP for every single one, I'll do DP at length of nums minus 1, and I'll be like, hey, that'll be the best answer up to the very last element, so therefore the best answer. Or I can make this like, hey, DP at index I is equal to the best answer, but your answer must end at index I, right? And then it's like, okay, the best answer, right? The shortest subarray must end at some index inside of here, right? So if I take the best one out of all the ones that end at a certain index, then that's good, right? Now the only thing is like, okay, I need to make this O of 1 operation in between, right? Okay, so here we can say returns length of shortest non-empty subarray of nums with sum of at least k, or -1 if none exists, that ends at index I. There we go. So that's the extra condition here. Okay. So let's make it. I think it'll be more useful this way, where it's like, you know, here it's like we can say, hey. Here we can say return min of self.dp of I, for I in range length of nums, right? So like that would essentially be the idea to the solution. Okay. Now for dp of index I, right? So we want the best subarray that ends at this index, right? Now, okay, I is equal to 0. Then we'll do return 1 if self.nums of 0 of I or is greater or equal to self.k. Okay. Here we'll just say like, hey, nums and k is equal to self.nums and self.k, right? There we go. So if nums of I is greater or equal to k, else -1, right? So if we're the very first index, right, there's only one of two cases. Either it's like, you know, the only number that's there is greater or equal to k, so we return 1, or it's like not greater or equal to k, and since we want to end at the very first index, that's the only number we can pick, so it'll be -1 in that case, right? Okay. But now it's like, do we want to use the previous results, right? So prev is equal to self.dp at I minus 1, right? The only problem I might need to initialize them, right? Okay. The reason I was thinking binary search, yeah, this is unfortunate. Okay. Prev is equal to self.dp of I minus 1. You can also read a protein by well meta or X, by the way. Very, very good. Very high quality stuff. I'm trying to think, right? Because we could have -1 as a result, which is very annoying. If we have -1 as a result, we're essentially forced to recompute everything, right? Is it binary search? Like, essentially, it's like in O of one time I can look up if an index works, right? So I might as well make it work, right? But then I'm not leveraging the idea of DP at all. Aye. Right, because it's like, if I'm not going to build the results up on top of each other, and I start doing O of n squared work inside of here, because I don't know if I can get away with log n. Can I in log n time search, the optimal index, where it's like, if it works for a certain index, right, it's like if I have a current j, I'm trying to search for like, you know, the largest I that works. It's not like a necessarily sorted array, right? It's like you might have even bigger arrays that actually don't work, right, because of negative values. So it's like, yeah, you cannot binary search over the space because we have negative values, which makes this annoying as heck. Okay. It's just, yeah, DP feels very natural in a lot of ways. It's just too slow asymptotically. I cannot write an n squared algorithm because of these bounds. I cannot write an n squared algorithm. I need to find a way to do this in O of n. And O of n log n doesn't seem like an option. Sorting doesn't make sense. Binary searching doesn't seem to be a sorted array of booleans, right? The point is that, like, you know, you might have an array of length 4 that works, and then an array of length 6 that doesn't work, because the two elements before the hand happen to be like negatives and so on, and there you go, bada bing, bada boom. So that's just not fortunate, right? And if I start looking at every index beforehand, then I'm doing no better. Like, best case is like, you know, like some result like this works, and then it's like, yeah. So there's got to be some sort of like 2 pointers or sliding window idea here. It's like, what do? You go from the beginning, you increase, right? Until you find a subarray of length k. And it's like, what? You start like decrementing your left pointer while it still works? I guess that would make sense, at least, just because it's like, okay, if you found a solution that works for a specific L and R, right? You're not going to start looking for solutions with R and R plus some K, right? Like, these will end up being bigger arrays, right? Is it really something that simple, though, for LeetCode hard? For LeetCode hard, I mean, I might as well try it, right? I mean, now we have O of 1 lookup. We might as well try it. We might as well try. Because, like, yeah, like, one thing I was worried about is, like, right, like, if you start, like, you know, if you find a solution and then you start, like, incrementing your left pointer, it's like, what if you need that left pointer for other solutions and so on, right? But even if there are other solutions, no, because then, like, you know, if there was a better one, they would have made you increment the left pointer anyways. It's like, if you find a solution L and R, you have no business incrementing your R, right? Like, you should be incrementing your L as tight as you can until you no longer find a solution. Because again, like, any solution that you increment this with will just make things worse. And in order to make up for it, you have to advance the L pointer anyway. Although, okay, maybe a good point, though, is knowing where to stop, right? Where it's like, now, well, I guess when you just don't have a sum of length of at least K. Okay, let me do this. Okay, it probably won't work, but we might as well try. So cur sum is equal to 0. We'll say L and R is equal to 0. While cur sum is less than K, 0, 0. Cur sum plus or equal res equal to float of infinity, while, yeah, so now it's like, Maybe it's like, okay, let's make our L equal to 0 here. Let's say, you know, for R in range, this is the way the LeetCode does things, right? For R in range, length of nums, right? Curse sum plus or equal to nums of R. While while curse sum is greater or equal to k, res equal to min of res, and what we'll do like R minus L plus 1 or something. Right, like here it'll be 0 minus 0 plus 1, then we'll say curse sum minus or equal to nums of L plus or equal to 1. And here while L is less than R and curse sum is greater or equal to K. Return res. Let's try something like this. Okay. Here we return null. Interesting. What? Null? Why are we returning null? What the heck is null? Oh, float of infinity. Float of infinity, else negative 1, right? So here it's saying it thinks it's negative 1. So, okay, here we'll do while L is less than or equal to R. Maybe that works. Okay, let's try submitting this. Okay, so here we got a wrong answer. But okay, we got to 61 out of 98 test cases. That's really good. Okay, so now it seems like we have an overestimate. Okay. So yeah, so here 167. So what? Okay, let's open up our terminal here. 95 plus 40 plus 32. Python 3. Oh, is it just that we need a case for the very end here? Here we'll say if L less than or equal to R and curse sum is greater or equal to K, res is equal to min of res R minus L plus 1. Does that work? No, it does not. Okay. Here, print L comma R at the very end, as well as our curse sum and our K. So what's it equal to? 32 plus 40 plus 95 is 167. 130 comes from where? 84 minus 37, 47 plus 32, 79 plus 40. What? How am I even having 130? What? Negative 37 plus 32 plus 40 maybe? Plus 95? Oh, I see. So I'm including this bad number. Maybe here we just do one last while loop then. We just do this. Okay. No. Interesting. So left, okay, so 1 to 4, yeah. Ooh, maybe we do and cursum is greater or equal to k, or nums of L is less than or equal to 0. Because if nums of L is less than or equal to 0, then it's worth getting rid of it, right? And then here, oh no. But then, yeah, we stumble across cases like these where there's a negative that we do want. Okay, again, so the negative values that are going to screw us here. Okay. We need an efficient way to do this, right? The point is that, like, between any two indices, we know how to get their sum in O of one time. It's just we only want to look at the ones that are interesting to us, right? And the point is that there's negative numbers here. Okay. Okay. Yeah. See, this is very interesting. Let's do something like this. All right? Okay. And then just remember what. Okay, let's submit this. Okay, here we have a wrong answer. Let's look at a wrong answer. So here it's thinking no solution. Zero and 4, and it thinks the current sum is what? How can it think that? Negative 28 plus 53 plus 33 plus 61 plus 32. 151. For every single number in nums, I will add to curse sum. Clearly this is never executed because my left is still 0. My curse sum What? What the heck? Sum is greater or equal to k. Yeah, this doesn't matter. Like 0 to 4, I should not be having a sum of 32. How is that even possible? Like this never triggers, or it does. Print, it doesn't even trigger. What? For come on, R. What is going on? It's negative 28, then I add 53. Why is it even 53 in the... What is going on to it? What? What? Okay, I add 28, it becomes 28. Then I add 53. Why is it 53? I say sum is equal to 0 at plus or equal. Like it's equal to sum plus nums at index r. Did I mess up? What the heck? What? What? For every index r in range length of nums, sum I add to it nums of r. How is it becoming just the numbers themselves? What is going on? Dude, okay, like I will do the same thing. Like sum is equal to 0. For nums, oh wait, this is my prefix sums. This is my prefix sums. Oh my goodness. Okay, this is not nums. This is not nums. This is not nums. Okay, this is not nums. Oh my goodness. Okay. Print nums. F string nums equals. Okay. I was like, what? That can't be what the code is doing. Okay. Okay, negative 21. Okay, so this is an interesting one. So the solution is to do this, right? Okay, so first of all, like one thing I can do is definitely ignore negatives on the left and right, right? Right. Okay. I'm trying to think of like a DP way to do this then. It's like at every decision I either choose to include a number or not, right? If I choose to include it, I increase my length. Right? Maybe it's like, okay, maybe we do something like that. DP old def DP self, I. If I in self.memo, then yeah, return self.memo of I. If I is greater or equal to the length of self.nums, right? Case 1. add index I to the current result. Case 2, make index I beginning the result. Prev is equal to self.dp. Okay. I don't know, so some trivial base case here. Here we'll do self.dp of I minus 1. Yeah, okay, I need some base case. But okay. Prev is equal to self.dp of I minus 1. Why is this complicated? Choose to add the next I to current result. Exclamation point. Prev is equal to self.dp of I minus 1. Stores the left pointer, previous left. Case 1 is equal to float of infinity. If self.prefix of I minus if self.get subarray sum from previous left to index I is greater or equal to self.k. Case 1 is equal to minus prev of L plus 1. Just no, this is not gonna work. Like, if I want to make it work, also, by just going through every element I can possibly go through, I'd have to make it n squared. There's got to be some sliding window idea where I can just lock in on decisions from the left-hand side. We could also do something like this. Nums minus 1. Sum is greater or equal to k. Min of res minus L plus 1. That's the nums of R. Curse sum minus or equal to nums of L. L plus or equal to 1. L curse sum minus or equal to nums of R. R minus or equal to 1. Can we do something like that? Yep, that makes sense. Okay, so that works for those cases, but does it work for every case? Is the big question. It is not, so we immediately fail another test case. Okay. Hi. Okay. Yeah. Yep. So it's like greedy is almost like not the solution here, right? 4 expected to. How do you do this without n squared? Okay. Maybe you do this for the entire iteration. Just like screw this stuff. Well, comma r is equal to 0, comma this. Equals sum of nums. Equals float of infinity. Okay. This would be like the 2-pointer idea. So yeah, 2-pointer idea doesn't work. Maybe while else less than equal to r. Okay. So yeah, this just doesn't work in this case. But we do get closer, which is interesting. So, oh, whoops. I'm getting a call. Okay, I'll be right back in 1 second. Hey there, I'm back. Okay, it is the new day. Yesterday I got a phone call from one of my friends to go to an event and so on that I was able to join and so on. So I had some fun with that. Yeah, so right now is the next day. And in fact, it is currently in 2 hours, there will be the new Daily LeetCode challenge, which means that if I do not finish this problem within 2 hours, I will lose this streak. Since this is a hard that we were struggling with, in fact, at the last hour, I end up still not having a solution. I think I'll resort to looking at the solution, so on, trying to make sense of it, and then using that for my solution here, just because it's like it would really be unfortunate to lose the streak because of that. So yeah, that's a little bit of an unfortunate reality. Hopefully we're able to solve this. I was indeed yesterday I was playing some board games with some of my friends, and I did think about this problem a little bit in the back of my head. So, okay, first of all, let's just remind ourselves what this is. Given an integer array nums and an integer k, return the length of the shortest non-empty subarray of nums with a sum of at least k. If there is no such subarray, return -1. A subarray is a contiguous part of an array. So, yesterday, I realized, like, hey, we can do this extremely easily with dynamic programming in O of n squared time, right? In fact, we can even do, we can get subarray sum. We can do something like as simple as this, right? So here we can, let's put these things away. We might as well, yeah. So let's populate, the prefixes and so on. We can literally just do, for I in range length of nums, for j in range, from I plus 1 all the way up to the length of nums. We can say, hey, here we'll have res is equal to what? Float of infinity, because we want a best solution. Here we can do return res if res doesn't equal float of infinity. Otherwise, there's no solution, so return -1. And then from here, it's like, okay, if self.get subarray sum from I to j is greater or equal to k, then here we can say res equal to min of res and the subarray length itself, which would be j minus I plus 1. And then return that, right? And so something like this would probably work. So it does not work with the very first case. So here's getting -1, so I'm doing something wrong. So like, yeah, so I plus 1. Maybe it's supposed to be able to consider itself. Yeah, so something like this works. And if we submit, since this is an O of n squared solution, the calls to this are technically O of 1, but still, this is O of n squared time. This is no bueno. We are going to time limit exceeded. 82 out of 98 test cases. And of course, with doing dynamic programming, you essentially just do the same thing. Overall, it's going to be n squared time complexity. This is too slow, right? And so we really realized, like, okay, if I do this with DP, even if I fixate the solutions to end at an index I, or I say the best case up to a certain index I, it'll either be the case that I need to do 2DDP, which is already n squared, or if I do 1DDP, I was really struggling to find a way to do it without doing some O of n work inside of the DP loop, even when I fixate the answer to end at a certain index I, right? Best case, I would be able to say, hey, from an index I, binary search between the indices before me to find the best one. But again, because there are negative numbers in this problem, that is no longer possible because we no longer have a sorted array, right? And so that's what I really was trying to fixate on last night, where it's like, because we have negative values, it really makes, you know, some idea like binary search from the DP side of things just kind of like not really possible, right? And that solution in the end would be O of n log n, right? Although if the numbers were just positive, you could probably just sliding window kind of thing. So I'll share what I was thinking of last night, which is like, hey, first of all, like, okay, realizing this, we want to have a solution that is at most O of n or O of n log n, right? Because something like n squared doesn't work, right? And so, and we know that like something like binary searching on DP, so like, you know, if we found the solution that ends at, the best solution that ends at index I for every single index I, then we take the best one out of all of those, right? But for each one of those, I need to essentially find the perfect before index, which is like, if it was just a bunch of sorted, you know, falses and trues, then that would be good. I can do binary search, but that's not really the case because of negative numbers. So if I'm going to do this in linear time, I'm going to need to find some sort of two pointers or sliding window algorithm in order to do this, right? Something along those lines, which means that at some point I must be able to force myself to make a decision, right? And so yesterday what I was saying is like, hey, if I have a solution that works for L and R, then there is no point searching for larger R's, right? And then we tried some greedy stuff and so on, and they don't work. So we gotta think here, right? Okay, so the question is, once I find a valid pair L and R, i.e. such that nums of L to R, sum of nums of L to R is greater or equal to K, do I increment L or R, right? That's essentially the golden question. This is the golden question. So let's think about this. So like case one, increment R. Case two, increment L. So what if, yeah, so okay, so something like greedy might not always work, right? Where it's like, okay, if you have a valid, okay, if you have a valid L and R window, or it's not, it's also two cases, right? It's valid or invalid windows. Okay, I'm already kind of disproving my idea from yesterday, so this is not good. Okay. I mean, okay, so cases like these are interesting, right? Where it's like you have to include the negative. It's like, let's think what these guys did, where it's like, okay, you keep the 2, and that's obvious, right? Like, you've kept the 2 up to this point. And then it's like, okay, you keep this. You're keeping this positive sum, right? 2 and negative 1 makes 1. But you're doing it at a price, right? You're doing this at a price. You're doing this at a price of an array of length 2. You're using 2 whole elements right now to get a length 2 array. This is very interesting. Okay, but you commit to that. It's like, how would you like? Yeah, this is tough. I'm not gonna lie, this is tough. So it's like, if I think in terms of okay, my prefix sums, ideally I want my L to be as large as possible. Right? I want my L to be as large as possible. So if I'm going to look for smaller L's, it really needs to pay up even more. Okay. We get a subarray sum. Yeah, we do self.prefix nums of j minus self.prefix sums of I minus 1. It's like really, it's like we want to maximize this and minimize this, right? Not really. Well, that's not, no, not really. Again, we want to be at least of size k in sum, but minimize the length. That is really annoying. And there's negative numbers. Usually when negative numbers cause issues, you can get away with using DP. But here's like any DP that I'm thinking of. Maybe the solution really is DP. It's just that every single DP idea that I'm trying to think of are all n squared. And one is n log n, but I think it's incorrect. So it's not gonna work. Okay. And there's okay, there's no hints for this problem. That's a bummer. That's a big bummer. Okay. This is a tricky one. This is a tricky one. I guess I was not thinking hard enough last night. Okay. Sorry, gotta drink a little bit. So what am I missing here, right? Where it's like, okay. Like, okay, if negative numbers didn't screw me over here, what I would do is like, you start with LNR at 0, you build a window as big as possible until you get to a sum greater or equal to k. And once you get to that point, you increment left as long as it still makes it greater or equal to k. Right, keep updating res, so on until you get to a point that's not greater or equal to k. Then you increment r and so on and so on. So how do negative numbers screw me now? How do they do it? Where it's like, I get to a point. Okay. So the first time I can definitely do that, right? I get to a point until the sum, or can I? Because now it's not like, okay, with positive numbers, like the thing that you have to keep in mind is that you can only make your things bigger, right? So it's like your sum can only become bigger over time. Here, with negative numbers and even zeros, this becomes really annoying, right? So you don't want your right pointer to go buck wild if you're not incrementing your values. It's like you want to skip over negative numbers, right? So do we want to skip negative prefix sums? Man, this is starting to get complicated really fast. Okay. If I have left and right, let's say I don't know the k, if it's greater or equal to k yet, right? So like I have some example. Let's take one of these beefier examples. That's a little bit too beefy. Maybe something like this. Yeah. So something like this. It's like my L, we'll say, is here. My R is here. So my current sum is what? So we'll do 84 minus 37 plus 32. I got a Python 3. Okay, 84 minus 37 plus 32. So it's 79. And what is k in this example? K is equal to 167. 7 curse sum is equal to 79. Right? Here the choice is kind of obvious. Ish. Okay. I gotta realize this, right? Where it's like, I can choose to bring my L to the R, right? But do I want to? Not really, right? Because, or That's the thing that's annoying, where it's like, oh yeah, this is a positive sum, but again, you're doing it at a price. You're doing an extra length of 2 in order to get this positive subarray sum. It's like you're not getting that for free at all. So you can't just make some like hard decision like, oh yeah, this is positive, I'm gonna keep it, because it's like, what if it's bad, right? Like obviously, if this is negative or 0, then it's like definitely don't keep it, right? There's no reason to. But then when this is a positive sum, so maybe this is where the DP part comes in. Maybe this is where the DP part comes in. Where it's like either you keep this or you don't, right? But then no, then it's two-dimensional DP. It's where the left and right pointer and squared. Jeez. Yeah, okay. I see why this is a LeetCode hard. Jesus Christ. Okay. It's like, man, I'm it's like almost every idea, it's like it seems so promising and then it just slips away from my fingers. What can I do? So like yesterday we tried, greedy approaches with 2-pointers and so on, and all of them kind of an edge case where it fails upon. What am I missing? What am I missing? I really wish there were hints for this problem. That would really be nice. That would really be nice. Hints would be nice in this one. Yeah, 31% acceptance rate. Turn -1. Yeah, because, okay, yeah, if all the numbers were positive, it's like, yeah, you build a window until it becomes valid, then you constrict it as much as you can, and there you go, that's a potential solution, keep going, and so on. Negative numbers make my life miserable. Because, again, the point that becomes really annoying is, like, here's a subarray, you're going to pay a price of length 2 for it, where you're going to include a negative number, but the overall sum is positive. Do you keep it, or do you don't? And k can be up to 10 to the 9. So yeah, if I include k in my DP and I update it, then it's just, that's no good. And also, yeah, if I don't solve this within the next 2 hours either, I lose my daily streak. And no hints, no nada. I might be forced to look at the editorial at some point. I'm trying to think. Okay. So why does this screw me over, right? Where it's like, I don't know if to keep it or not, right? I'm paying a price of length 2 in order to keep this. It's like, I gotta know, like, will I need this sum later on, or can I ignore it, right? But the point is that, like, if I don't make a decision now, then how can I do this in linear instead of n squared time? Like, I need to be able to make a decision. How can I make a decision? I need to be able to make a decision. How can I, like, for example, in this one, is it the entire array is what's needed? What's the sum of this? Oh my gosh, okay. Sum of this guy. No. 32 plus 40 plus 95. Yeah, so you just need the last 3. So yeah, so here's a case where it's like, yeah, this had a positive array sum, but again, rightfully so. You paid a price of length 2. You needed to make a decision to move the left pointer here. But how the hell did you know that? How did you know to move the left pointer here instead of keep trying to look for more elements because this was a big sum? Okay. So somehow I needed to know to move my left pointer here. How could I have known that? How could I have known that? How could I have known to move my left pointer here? How could I have known this? -84. It's just like that's such an annoying dilemma. Like, how do you make a decision? Like, what if the sum had been 168? All of a sudden, it's like I know that this is not. It's as if though I needed to check like this rest of the sum here, so on, potentially with negatives and so on, resolve the same problem. Okay. It's like I would have needed to solve the problem for here. And then from that point on, I'd be able to tell myself, like, okay, if I start from here, I can add this much of a sum. Do I need to? Yes or no? Okay, maybe that's a DP kind of idea, right? Where it's like, I need to take... Oh, man. No, but the point is, like, I need to do this for every single right pointer, of which there's O of n many. All the DP solutions lead to O of n squared. It's just crazy. Okay. Right. It's like it knew. And then if this was a 168, the answer would have been 5. So then you handle both these cases. So in fact, I should make another case like that. Where it's like, it'll be, yeah, we'll make another case. Case 4 and case 7. So we'll make this 168. So we need to pass both of these. Right? So the answer here is 5. And yesterday we tried greedily doing 2 pointers, right? Yeah, take the whole current. Yeah, it's just you don't know where the negatives in the middle are. You can't really just tackle down things from the left and right. You don't have enough information to make decisions like this. The only way that like you could really capture information like this is by using prefix sums. Because then it's like you have the sum of all of the remaining numbers, and so it's like, yeah. Maybe that's the idea. Okay. So some sort of, okay. The greedy approaches really aren't working. So this is really the first, like, this is one of those, rare cases where it's like, a minimization problem. Well, okay, it's not that DP doesn't work, right? DP does work here, it's just too slow. Okay. So like usually I say like, hey, for most optimization problems, especially on LeetCode, you can either resort to greedy, divide and conquer, or dynamic programming. Dynamic programming here does work, it's just not optimal. kind of, if I have my right pointer here, let's think about it. The prefix sum of this gives me 214. Prefix sum of this gives me 0. This is valid, right? Maybe it can be like, hey, what is the loss in sum that I will yield? Well, sum of this minus sum of that is just an element itself. So that's essentially what I was doing, right? And greedy doesn't work. Okay, this is when I really need a hint. Like I've generally tried, like most of the things that I can think of. DP is too slow, greedy doesn't work, 2 pointers doesn't work, sliding window is flawed. Like it's like I have a bunch of like, you know, tricks up my sleeve, and I use them all up, and now I don't know what to do. It's like and the worst part is I'm probably missing something so obvious. It's like negative numbers. Okay. Yeah, this is when I need a hint, right? It's just like I don't know what direction to go. It's like I'm convinced that I'm gonna need some sort of sliding window approach, but how do I make a decision, right? Like how do I make like based on this length 2 array, it's like, you know, it has a positive sum, which I might need, but at a price of 2. And if DP is too slow, and it's like, you know, if K is 168, then the answer would have been don't ignore these two. If it was 167, just one less, I would have ignored these two. So, okay, so maybe I need to make my decisions based off K, but then the point is that if I'm doing sliding window, I don't know what the hell the rest of the sum is, right? The point is I'm trying to make this algorithm more linear. Well, actually, I do know what the rest of the sum is. Okay. Whoa. Okay. Maybe I'm onto something here. I do know what the rest of the sum is, right? If my R is here, the rest of the sum is get subarray sum from the length of nums and this, right? But again, there could be more nested negatives in there. Oh my gosh. I would need to solve the problem from index R onwards. And then check if the solutions. Oh my gosh. This is too much. It's just like it doesn't make sense. Okay. I'm also getting nervous about the 2 hours. I want to make sure that I have that I'm prepared for the next day lead today, and so on. Have enough time to explain, upload the video and everything. It's already like super late. Okay, maybe I wish there was a hint that I could look at instead. Okay, maybe we look at the tutorial. I'm just pretty curious at this point because I am pretty stuck. So let's just do it. I don't do this often, but you know, today's gonna be one of those days. Let's just do it. Okay, solution overview. We are given an array nums that contains both positive and negative values along with an integer k. Our goal is to find the shortest non-empty subarray whose sum is greater or equal to k. This problem is very similar to 209 minimize size subarray sum with one key difference. We have negative values here. We strongly suggest solving the original problem first, as our solution will build upon that approach. Okay, okay, you know what? Let's do that. Okay. 209 minimize subarray sum. We have never solved this before. Okay. Given an array. Okay, so given an array of positive integer nums and a positive integer target, return the minimal length of a subarray whose sum is greater or equal to target. If there is no subarray, return 0 instead. Oh, okay. Okay, so here the sliding window idea does work. And here they say our solution will build up. Okay, so the solution will, okay, well, let's see, let's confirm, right? So here it's like, okay, so this seems like to be legit the same problem, right? Given an array of positive integer nums and a positive integer target, this is our k now, return the minimal length of a subarray whose sum is greater or equal to target. Okay, so the point now is that like, if we increase our index r, we're always like guaranteed to be, you know, with a positive, like adding to our sum. There's not even zeros with their left pointer. We don't have to worry about negative. Okay, so we can literally just do something like r is 0, 0. And then we're gonna say, or we can just say L is equal to 0 for R in range length of nums. Sum plus or equal to nums of R. We will say res is equal to float of infinity. And here we'll say return res if res is equal float of infinity, L0. Sum plus or equal to, wait, minimum length of a subarray. Can target be, okay, target is at least 1, so we can't do a 0 length subarray. Okay. For R range length num, sum plus or equal to nums R. While sum is greater or equal to target, res is equal to min of res and R minus L plus 1. Sum minus or equal to nums of L. L minus or equal to 1. L plus or equal to 1. Right, so this would essentially be my solution here. Okay, so that works. Okay, so that works, and there we go, 60%. Okay, bada bing, bada boom. Okay, so, okay, we know, okay, so, cool, okay. The problem is very similar to 209 with one key difference. Okay, so now we have negative values here. Okay, so here is a LeetCode medium. Essentially, it's like, okay, makes sense. Oh, if you figure out the O of n solution, try coding another solution which of the time complexity is n log n, so do it worse. Okay. Why? Of n log n? Oh, maybe this is where the DP idea comes in? Or oh, okay, wait. So, holy crap. Okay. That's an interesting challenge. I mean, like, you know, technically something I can do is like, you know, nums.sort, and there you go. This is a solution that works, that is n log n. Right? But obviously that's not what they mean. Well, it's weird to ask you to do something worse. But maybe there's a learning outcome. Are there any hints? No hints. This is a weird follow-up. Make your solution worse. Like they want you to do this in O of n log n. Sorting doesn't make sense because you want subarrays. So it's like you want up to a certain index I. So why can't I do binary search in the original problem? Oh, I can't do it because of negative values, right? Okay, so here, maybe we can do def dp, self and an index I, right? And here we'll say, okay, self.nums, self.target is equal to nums and target. And here we'll say nums, target is equal to self.nums, self.target. And here we'll take, for my DP, let's do this. Yes, this will work. Okay, this is exactly my idea, right? The point is like, okay, so this is the best solution that has an index I. Now we do have a sorted array of falses and trues because we, like again, because when you add numbers, you can only make things bigger, right? And so it's like some index L is either going to cause me to be greater or equal to target or not. And it's going to be like, I'm not greater or equal to target until some point I am greater or equal to target, and everything will always be, right? Because the point is like, you know, if your number is too small and you're not greater or equal to target, you can keep incrementing, well, at the very beginning, it's like you'll have all these numbers, right? And so it's like, okay, you are greater or equal to target, but the more that you squeeze in your L pointer at some point, you will no longer be greater or equal to target, right? You want to find the tightest L such that you still are greater or equal to target. So you want to find, so you'll essentially have a bunch of truths followed by a bunch of falses. You want to find that rightmost index of a truth. Okay. This will make sense. And so it's like here we can just do return. So this will be the answer, the best answer ending at every single index I. The answer will end at some index, so we return the best one, right? So return. Here we can do res is equal to float of infinity. Brian range length of nums. Self.memo is equal to this, by the way. Case is equal to self.dp of I if case doesn't equal -1. Res equals min of res, comma case. And here return res if res doesn't equal float of infinity. Else 0 in this case, actually. Case is greater than 0. There we go. Okay, now yeah, so here we'll do the things. Okay. So we're at an index I, right? The point is we're gonna binary search on our left here. Actually, okay. So one thing we want to do is we want to build our prefix sums, right? So let's do that. We definitely need that. I'm just gonna steal my own code. So let's just, yeah. Right here. We want to keep that. Okay, this I want. So the target is equal to the target. There you go. Okay. So now we've got our prefix sums. I'm gonna take my same function though. So get subarray. These are all useful. Okay. And so the point now is that I can binary search. Then the only thing is like if I'm at the very end, or if I'm at the very beginning, I is equal to 0 is less than or equal to 0. First of all, assert I is equal to 0. If I'm at the very beginning, right? 1 if nums of I is greater than target. L0, right? Just of length 1 if that number is greater or equal to target. Okay. Otherwise, it's like, hey, we have some index I. Idea: binary search for tightest index L such that sum of nums of L to I is greater or equal to target. 0. Okay. This will be sorted array of true, comma, dot, 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 comma, true, false, comma, dot, 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 comma, false. So want rightmost true. Okay. So here we'll say L, comma, R is equal to 0, comma. We could have the number itself. Yeah, if a specific number, you know, if just one of the numbers, okay. Actually, here we can say, hey, cover the case of just one number already being greater or equal to target, right? So like nums of, yeah. So if max of nums is greater or equal to target, return 1, right? So now it's like no singular number is greater or equal to target, right? So here it's like I can essentially just remove this and do return 0. And then here I can just do all the way up to I minus 1, right? Already checked that no singular number is greater or equal to target in nums. Okay, so L, R is equal to 0, comma I minus 1. R equals I minus 1. And not I, since already checked. Okay, there we go. Well, L is less than or equal to R. Mid is equal to L plus R over 2. Then we'll say, hey, rightmost index is equal to L. First of all, if sum of nums L to the I doesn't work, then no solution will. Right, because this is the biggest. This is because this yields the largest sum. So if prefix sums is equal to self.prefix sums, right? And we already, okay. Prefix sums, if prefix sums of I minus prefix sums or just prefix sums of I is less than target, then return 0. Right? There you go. Otherwise, yeah. Otherwise, find tightest index. That still makes some greater equal to target. Okay, well, L is less than or equal to R, mid is equal to L plus R over 2. And then we're going to say, hey. Okay. We're going to say, okay, rightmost index. Rightmost index is equal to L. Yeah. If yeah, you can get subarray sum. Self.get subarray sum from L comma R. Yeah, so here if we can just do, right, 0 to I. Here, if self.gets subarray sum from L to R is greater or equal to target, valid solution. So update. This is our first res, right? And check for even tighter solutions. So this will mean like L is equal to mid plus 1. And this will mean res is equal to mid. We'll call this rightmost index. And just in case, out of paranoia, we'll do max of rightmost index and mid, which should always be the case. Otherwise, invalid solution. I subarray too small. So need to make it larger by making window larger, i.e. by decrementing left pointer earlier / smaller. So here we'll say R is equal to mid minus 1. Right? So now we have a rightmost index. Here we'll say, first of all, if I in self.memo, turn self.memo of I. Right? There we go. And here we'll say res is equal to So this is the rightmost index that works, so it'll be I minus rightmost index plus 1. Self.memo of I is equal to res, turn res. This does not work. Uh-oh. Technically, I'll just do that. I'll do that. Interesting. And I definitely don't need this check anymore then. That's fine. Just making sure I'm not missing anything. I think I'm making a mistake here, right? I don't want, actually, yeah, so let's be careful here. This should be mid, right? If from mid in R, if this is greater or equal to target, then great, we'll make it mid, right? So now what's going on? Mid is equal to this. Yeah, okay. I should be including index I. Of course I should be. Right, but what I'm saying is like, okay, if this is an L, right? If this is L, this should still fail. Like we might get correct solutions here, but I expect a wrong submission here. Right. Now if I make this a mid, and I use this test case, do we pass it? We do indeed. Right, exactly. Okay, okay. I'm not tripping. Okay, but now we fail this test case. We got a 9, 7, 8, bada bing, bada boom. So here I can also remove this. I could just do that. Okay, and we still get a wrong solution here. So this is interesting. Here, okay, I might as well keep that, right? That's just an extra O of n check. I might as well keep that. Put as 9. Yeah. And set the Subarray sum just to make sense. Yeah, we'll return that if that is the case. Yeah, if my current index mid. Oh. Maybe I should make this my I. Yeah, okay. Okay, that makes sense. Okay, there we go. So this, okay. So there we go. So we have an n log n solution that works with the exact dynamic programming and binary search idea that I was talking about, right? Where it's like, okay, we will find the best answer that ends at every single index I, right? And for an index I, what we will do is like, hey, we will binary search to find the tightest, essentially, element before index I that will give me a subarray sum that is indeedly valid, right? And the point is we can leverage the fact that, like, you know, the wider you make the gap, the larger the ending result. The tighter you make the gap, the smaller it is, right? But when you have negative numbers, it's like, you know, it's more like, you know, it can be random. It can like go too small, too big, too small, too big, da 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 da. But when it's all positive integers, it's like the wider you make it, the bigger it is. The tighter you make it, the smaller it is, right? You want the tightest, you know, working solution. So it's like, you know, you start from here, you have your middle one. It's like, does this work, right? If it's too small, you need to make it a bit bigger, even though you'll have a larger result, right? If it's good enough, then it's like try to look for even tighter solutions. Otherwise, keep track of this as your current best solution, etc., 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 right? So it's like you binary search for every single index I, and then once you're done with that, you essentially have the best result possible for every single index I. And so you know that the solution will end at some index inside of the array, right? So the optimal subarray will have to end at some index. So between every single solution that ends at every single index, you take the best one, right? And there you go. You have the solution to the original problem, right? And so, okay. So that is essentially how I would have done it in O of n log n. Not sure if that's how the expected solution was for this case. So, okay, let's take a look at the editorial. Okay, so sliding window, that's how I did it. O of n at the very beginning. And then, oh, they're not going to share how they did this in O of n log n. What? But they had a follow-up. Okay. Okay, so they had a follow-up about how to do it in O of n log n, but they don't show it in the editorial. Okay, oh well. I mean, the sliding window, okay, pretty trivial. Or pretty intuitive. Yeah, okay. Okay, so this is like, I was kind of proud of this, where it's like, I figured this out. DP ends at every single index, and binary search for the remaining results, and it does work in this case with positive numbers. It will not work inside of this problem that has negative numbers. Okay, so now we can go back to looking and reading at the editorial. So okay, so we've solved this problem, and okay, so it's like we strongly suggest you solve the original problem first. Oh, great, we know how to solve it with sliding window. That's completely okay, and we know how to do it with dynamic programming with binary search inside of each column. So there's O of n total things that can go into my memo, and each call to the DP will be O of log n work. So the overall time complexity of this solution is O of n log n, right? Because I will do at most n calls to DP, right? Because there's at most n index i's, and for each one I do log n work, right? So it'll be n log n total worst case overall asymptotic time complexity, right? So that is an n log n solution. Okay, so the original problem was using a variable length sliding window. Cool, but that approach will no longer work here. Right, let's take an example to understand why. Consider nums is equal to 2, -1, 1, and 3, and k is equal to 4. Let's walk through a naive variable size sliding window approach step by step. Start with window 2. Sum equals 2, not greater or equal to 4. Okay, expand to 2, -1. Sum is equal to 1, not greater or equal to 4. Expand to this, yeah, so while it's not greater or equal to 4, you keep expanding. Sum equals 2, not greater or equal to 2. Sum, yeah, okay. Expand, sum is greater or equal to 5, greater or equal to 4. Okay, so now you'll start, decrementing the left pointer. Now we try to minimize the window size by shrinking the window. Yeah, absolutely. Remove the first element. Window is this. Sum is equal to 3. Not greater or equal to 4. The sliding window now stops because it assumes reducing the window further would only decrease the sum value. But it doesn't, because if you get rid of this, you get rid of a negative that actually makes your thing bigger. However, if it shrinks once more, remove the second element. Window 1, 3, sum equals 4. Right. Okay. We find that our condition is satisfied again, and we find our required answer. The negative value, -1, breaks the monotonic sum property that a standard sliding window relies on, making a simple variable length sliding window approach unreliable. Okay, so this is not news to us. Okay, so let's keep looking. Priority queue. Okay. Okay, so heaps are in this problem. I did not think about heaps in this problem. Okay. Sorry. Okay. The brute force approach would be to loop over all subarrays and nums and check if there's sums. Okay, okay, sure. The smallest one among them is our answer, right? However, this approach is too slow for our constraints. All right, okay, absolutely. That's n squared. Let's identify the even if you do prefix sums, right? And it's like, you can, in O of 1 time, you're able to get like essentially I have this get subarray function, get subarray sum, so you can give me an index I and an index j, and it will return to you the sum of that subarray in O of 1 time. But even then, that's too slow. Let's identify the redundancies in the above approach. One major issue is that we keep recalculating the same subarrays multiple times. We can solve this by creating a prefix sum array. Okay, well that's not obvious. I mean, like, even doing this, it is still too slow, which lets us quickly find that, yeah, using this array, we can look at each element and find an error. Yeah, when subtracting from our current sum gives us a value of at least, okay. However, searching for the best prefix sum for each index is still too slow. Exactly. What we really need is a way to quickly find the best prefix sum, one with the lowest value that's also closest to our current position. Okay, but again, it's like, how do you know, like, hey, a subarray sum, this one's positive, this one's more positive, but if you pick the more positive one, then it's like, it's of higher length, so it's like, do you sacrifice a higher length for more sum that maybe you need, maybe you don't? Like, that's gonna, what does best mean here? What we really need is a way to quickly find the best prefix sum, one with the lowest value. It's also closest to our current position, but again, you don't know what you need to know. This is where a heap, also a priority queue, becomes useful. Okay, we can store pairs of prefix sum ending index in the heap, arranged so that the lowest sum is always at the top. Okay, this helps us quickly find the best previous sum to use. You want the smallest prefix sum? What? Okay. Okay. Let's loop over the nums array now. Keep track of the running sum in a variable called cumulative sum. We'll also keep track of our result in the variable shortest subarray length. If the cumulative sum meets our constraints, we consider it as a potential result. Otherwise, we'll loop over the top elements of the heap while the difference between cumulative sum and the sum of the top element is greater or equal to k. For each such element, we check if it is the minimum length subarray we found till now. After checking an element in the heap, it can be discarded, since all further sums in the loop will result in longer subarrays. Holy crap. So it's like, okay, so this is where the decision is being made. They're essentially saying it's like, a solution must start at an index. Coming from the beginning, you only consider, oh my god, okay, holy crap, okay, from the beginning, so okay, so it's like almost like a concurrent queue. It's like it's like oh my gosh, okay, so it's like you have n things in a heap. Okay, the heap one is just to be able to have the minimum one. We can think about why that's useful. The important point is, like, you have n choice. You have n things that are still up to grabs. While that is greater than 0 in terms of length, you have stuff you can subtract. And the point is, you go from the beginning of the array, right? And that's like, once you get to a certain point in the array, it's like, okay, I can only consider things that are before me to subtract, right? And if I can consider something before me to subtract, I should, because that's when I get the minimum possible length. So right. If I can, if I'm at an index r, and I find something that I can subtract with before me to get something that's greater or equal to k in sum, then I should expand that one starting index with this one, because it will not make sense for anything else. Jesus Christ. Okay, well, I mean, that makes a lot of sense. Okay, I don't understand the heap part of it yet. We can think about this a little bit. Okay. Okay, wow. So this problem is a whole lot more packed than I thought it would be. Okay. Okay. This is one of those problems where you learn a lot. Okay, this is good. This is good in a way. Also, okay, so I have an hour and 15 minutes, really. Okay. So essentially, this is wild. So you keep every single prefix, and so let me think. It's like when you go from the beginning of the array. No, this is illegal. Holy crap. So like the point, it's like when you're at the smaller indices for your right pointer, you want to force solutions there if you can, because you're as small as you'll be. So if you can grab a solution, you should. And so this is how the decisions get made. Geez, okay, this is like a way out of the box solution that I was just not in the like galactic universe of thinking. This makes complete sense though. Holy crap. So it's like, okay, the really the idea that's going on right now is that, yeah, if you're at a small index R, you want to force solutions at that index R if you can. Once you can't, then it's like, okay, I can't do any more solutions here. Let's move on to a bigger index R where I might be able to, right? Not because you might get bigger sums and so on, whatever, that's the hope. But the point is that, like, if you can't find a solution at the current index R, that's how you get the minimal length 1, right? It's like, if I'm using up a starting index, I might as well use that up with the smallest possible right index, right? And so you might as well start with a right index at the very left. That is insane. That is actually insane. Okay, and so the way you know that if something is good enough is if you take the prefix at a certain index. This is just wild. You know that if you don't even need a heap. Like the heap is just it being like, you know, fancy stuff. I mean, okay, the heap does allow you to be just better in terms of type complexity. Well, the point is like the point is like you have n elements and you'll end up using them all at once. But technically, if you never use them up, you never use them up, you end up doing O of n work all the way up to n squared. It's just like with the heap, at least it's like if the first one doesn't work, then you can just skip. Yeah. Oh my gosh. Okay. Yeah, the idea makes sense. It's just that, yeah, this is why hints are necessary, because it's like, now that I got the idea, I wish they didn't tell me the thing to do with the heap and so on, because it's like, I don't know if I would have been able to come up with, like, you know, putting prefix sums into a heap, right? That makes a lot of sense, though. It's just, yeah, that is a wild solution. I mean, okay. Yeah, I don't want to, okay, again, when I read the editorial, though, I want to read as little as I possibly can, because I want to treat it more as a hint than I do a solution, you know, thing. It's just, I really only resort to that if there are no hints, like is the case with this problem, and I'm kind of stuck, which I was. Okay. Man, what a wild one. Okay, and we have an hour, okay. So yeah, so we could just do, you know, a heap is equal to, oh, Jesus Christ, okay. So we'll do, yeah, we need to know the indices of them all. Okay, for now, I'll just, you know, let's not be annoying. We'll just do prefix sum, comma I, for I, comma prefix sum, in enumerate prefix sums. Heap u dot heapify heap. This is a min heap. Man, what an idea! What an idea! That's like, honestly, what an idea. See, that's a pretty cool solution. I'm not gonna lie. Like, again, it's obvious, right? It's obvious in that, like, somehow you need to force decisions, right? Here, it's what they're doing is they're like, instead of the O of n work instead of the p, it's like, yeah, there's O of n work, but I can make it O of n work in total, not O of n work per call. Yeah. I need more practice. I need more experience with LeetCode. That's really like the only way. It's like these are clever solutions. I just need to see these types of ways of solving a problem more often, because they're pretty cool. I'm not even gonna lie, they're pretty cool. Those where it's like, it's like O of n work, but in total of n work, and so therefore it's like, you won't blow yourself up, right? It's like, those n squared loops, but like it's actually all O of n, because it's like one of the loops, like you'll only end up iterating a total of n times over the other ones, and like, yeah, like that type of pattern is like, it happens sometimes, and I need to be better at recognizing it. Okay. But yeah, let's keep going. This doesn't feel like a complete failure, right? I mean, again, like I had to get some help, but I'm kind of proud. We solved this medium problem in both the O of n and O of n log n way, so that's very cool. And so yeah, so honestly, this is a good challenge. Out of all the LeetCode problems, this is one where I learned quite a bit, so I can't be too mad about it. But okay, let's keep going. Yeah, okay, so now we have these things, right? Idea. Go through every index R for each one. If you can have a solution. Yeah. I'd have to explain this. Yeah. Go through every index R. Yeah, so the point is that, like, when you get subarray sum, you want the one that's small. Yeah. Okay, the min heap, I'm not gonna lie, is kind of genius. Okay, what we're just gonna do for R in range length of nums. We'll do sum comma index is equal to 0 comma 1. Well, self dot get subarray sum of min heap. We'll call this our min heap. Q.hipify min heap of 0 of index. So genius, man. Oh my goodness. Very good. Okay. Here we'll say prefix sum comma index is equal to heap q dot heap pop from the min heap. Res is equal to float of infinity. We'll do the same trick here, and then here we'll say, hey, return res if res is equal float of infinity, otherwise return -1. Here we'll say res is equal to min of res, as well as r minus index plus 1, right? This is a valid case. If a min heap greater than 0. There we go. If length of min heap equals 0, break. Okay. Okay. Also, the index has to be before R. Less than or equal. Yeah, so that didn't tell me much, right? With the main camp idea is like you have all these prefix arrays. Yeah, what if my R is just straight up not large enough? Yeah. So maybe I just do this. Here I'll just do print min heap. So yeah, the min heap still has a lot of stuff. So there's 3. Interesting. Right. Subarray sum between min heap and index and index R. Here at the end of the day, I have everything in my min heap. So here from this index, yeah, maybe there's stuff in my min heap that I actually want. But yeah, again, I should be deleting. Oh, well, first of all, I'm not doing this correctly. That could explain a lot of stuff. You know, okay, let's just keep reading this. Okay, in the heap, arrange so that the lowest sum is always at the top. This helps us quickly find the previous sum to use. Let's over the noobs. Yeah, keeping track of the running sum. Okay, sure. We also keep track of our result in the variable. Yeah, if the cumulative meets our constraints, we consider a potential result. Yeah, for each such element, we check out the minimum length found until now. Yeah. This is going a bit slow. Okay, I'm just gonna, there we go. Add your stuff to the heap. What? Oh, I see. I see. It's not quite what I thought. Yeah, with the heap problem, although okay. I want to try something else, right? What is a data structure where it can remove things very efficiently? A hasha, right? Okay, let's do something like this. I want to see if this is fast enough. Like we might get a very slow solution compared to everyone else, but I want to see if my idea works before I try implementing theirs, right? Here, what I want to do is this. For I, prefix sum, and enumerate prefix sums. Okay. I will say, hey, is equal to float of infinity for r in range length of nums. Length for, the thing is I want to loop over the dictionary keys and then delete some. Okay. Here we'll do keys to delete is equal to this. Okay. For key and keys to delete, del d of key. There we go. Okay. Here we'll say for key and d. We'll do loop invariant. All keys to delete dot append key. There we go. Okay. Let's go key. If for index and d, we'll say if self dot get subarray sum of for I and d. It's greater equal to k. Res is equal to min of res r minus index plus 1. Keys to delete dot append index. Okay. Okay, so this is accepted. And let's submit. We might, like, technically this is n squared, but it might be fast enough. Or wrong. Interesting. There we go. Okay, let's just make that an extra condition. Okay, so we still TLE. Right. Yeah, technically we're in squared. I thought maybe I could get away with it, but yeah, not really. Damn. Damn. Yeah. Yeah, I can't do that. That's a bummer. Yeah, so my idea does work. It's just this is too slow. And you can't find out in over one time that's the best one, right? Maybe you can binary search though. So it's like I can sort the prefix sums. Nah. Because I need one that's okay, another thing I can do is is equal to sorted of this. Prefix is equal to sorted. I will just say prefix sums is equal to this. I'll say that. For iron range length nums, we'll just say hey. While less than length of nums and prefix sums of sum, index equals 0, 1. Prefix sums of I of index greater than R. But then I need to be able to delete stuff. Yeah, okay. This is just not going to work out. Okay. So yeah, I think, yeah, so that is another idea that works, but that is, again, too slow. And that's kind of the model of this problem. Okay. Bummer. Again, we cannot make that decision over one time, which is just really annoying. So, but yeah, what they do is essentially, it makes sense, right? The point is that whenever they get a solution that would have worked essentially kind of like with sliding window-ish kind of a thing, like for example here, yeah, cumulative sum is equal to 3, which is greater or equal to k. Update short list like the 3. As soon as they find an optimal solution, they're like, hey, look for more, right? So like here at this point, it's like, yeah, check the heap. 3 minus 1 is equal to 2, which is less than k. So keep the element inside of the heap, right? Yeah, and then yeah, add some 3 and index 2 to the heap. Yep. Makes sense. Okay. So essentially it's like, Yeah, so they have a running sum, right? So the point is like kind of like a sliding window almost, except there's no really left pointer. Like left is fixed at 0. But that's like whenever they find that it's greater or equal to k, they're like, okay, we found a solution. Let's see if the smallest prefix sum that we can remove, which, because they're adding things into the heap in place, first of all, will guarantee to be of a smaller index. Very smart. And then check it like, okay, we might as well check the smallest one so far. But they don't check more than just that? Or do they, or should they keep doing that? Right, you might as well get rid of as many things from the heap as you can because they're all going to be the best solutions to your current index. Okay, that kind of makes sense. So, okay, we can try that. Geez, okay. Prefix sum of I, yeah. Actually, yeah, so we will not do that. We'll say min heap is equal to an empty array. We'll say, hey, for I come on num and enumerate nums. For R in range length of nums. We'll do the same trick as always, right? This thing. Okay. As equal to float of infinity. For R in range length of nums. Okay, and wow, the next LeetCode comes out in 45 minutes. Okay, we're doing back-to-back today. For R in range length of nums. We'll say, yeah. Prefix sums of R is less than K. Here we'll do min heap, heap q dot heap push min heap, comma, prefix sum is equal to prefix sums of R. Prefix sum, comma R. Right? It's not big enough. It will be used as leverage for another solution. Now, if it is, prefix sum is greater or equal to K. So assert prefix sum is greater or equal to K. I mean, this is just straight up obvious. Okay. Then now it's like while sum comma index equals 0 comma 1. I've typed that a lot of times. While min heap of 0 index is less than or equal to R, and get subarray sum of min heap of 0 of index comma R equal to K. Where is equal to min of res sum prefix sum is equal to comma index is equal to min heap q dot heap pop from the min heap will be R minus index plus 1. Okay. Min heap is greater than 0. And okay. Okay, let's run this. Right. Just like keep getting every one. Maybe, yeah, I should push no matter what. Here I should do this, less than R. And here I don't even need this technically. Maybe I can do that. But here I just do this. This is already guaranteed. Yeah. Interesting. So this just did not work. Really. Oh wait. Oh no. Interesting. So we pass a lot more test cases when I do that. But not all of them. Not this one and not this one. What if I push this first? Interesting. So now we pass everything. And there we go. Bada bing, bada boom. Okay, that feels pretty nice. But again, I cannot really take credit for that solution because it is just not my own. It is from the editorial. Rip. They probably did it in a much cleaner way too. Oh, there's more. Monotonic stack plus binary search. Okay. We can also implement this idea of using the best prefix sum efficiently using a binary search approach. Instead of a priority, let's maintain a stack-like data structure to hold the prefix sums for each index as we iterate over nums. To hold the prefix sums for each, okay. Yeah, sure. Each element of the stack will hold a pair prefix sum index. Okay. We'll maintain the prefix sum monotonically increasing. Wait, I was thinking of, okay. I was thinking of this idea after I read the editorial with the heap. Okay. The monotonically increasing property works because of at each step, all prefix sums which are valid candidates to be used. yeah, so yeah, this is something I realized, but after when I was implementing the heap thing, make this work, we start by updating the running total of each number of the array. To keep the structure order, we remove any entries from the top that are greater than or equal to the current sum. This approach ensures that both the prefix. Oh, I see. I see, but don't you want things like from the left? You want the smallest ones? Right? Like if you have like yeah. No, yeah, you can't use a regular queue, right? Because again, you don't know if the prefix sum you're adding is the largest one anymore. Again, there's negative values here. Okay. I don't think I get to be cheeky. The difference between our current position and the index we find gives us the length of okay, I see. Okay. Cool stuff. Okay. Yeah, but it's the same type of complexity. Oh, okay. Approach 3 deck. If we take a look at preview, we notice a recurring talent. We need this brings us to the question, can we use the dish? Okay, let's realize using queue. Let's just do it. Yeah, sure. In this case, our deck will hold the indices of the prefix sums that might serve as a starting point for our target subarray. We also make sure that these sums form a monotonically increasing sequence. Earlier prefix. Check if we can find valid subarrays. Okay, there's just a lot, but the idea is essentially the same and so on. Oh, okay, but they're able to do this in OVN. Okay, that's really cool. So hard for today, internally died. Try prefix sum for fun, expecting it. Because it would be a hard. Got smacked with TLE. Read the solution priority queues decks. Huh? Yep. Spent an hour debugging the code. What a whole new world to me. Keep grinding. The insight that you can discard each prefix sum after finding the first and next quiz. Yeah. Completely agree with you, Noah. Yeah. Thumbs up. Yep. Okay. Okay, yeah. Okay, I'll undo this just because I really want to emphasize, yeah. Completely agree with Noah here. The insight that you can discard each prefix sum after finding the first index that creates the window with some greater code K is freaking game changing. Completely agree. Realizing that thing was indeed very much game changing. So, Mr. Noah, completely agree with you. I mean, there's even replies. Yeah, I gave it thought and found it. Well, thanks. Because okay, they're not really on that comment. Yeah, this is an amazing comment. Okay, all right. But yeah, I mean, in hindsight, this makes a lot of sense. But yeah, man. Just okay. I mean, okay, we have a slow solution and so on, but I don't even mind. I guess this is like the OVN people. Oh well, and so I'm also doing a lot of extra work that I don't need to be doing. I have like this self-subarray function. I have a bunch of asserts and so on, but I don't really mind too much. You know what? I will keep all my work in here and so on because it's just this is not even my solution, so I might as well have stuff that I did right. I might as well just resubmit saying disclaimer. I came up with this solution only thanks. This solution wasn't found on my own. I had to make use of the editorial. Okay, so as always, in all my videos, I do a quick recap of how I was able to solve the problem. So for this one, I don't think I will spend too much time explaining how I was able to solve the problem. Thankfully, I was able to do so because in 30 minutes is the next daily. So, scrap the deadline there. But I tried a lot of things for this problem. I ended up trying dynamic programming, which did work, but every single dynamic programming attempt that I tried to do would end up in O of n squared time complexity, whether it's because I do 2D DP, which is O of n squared, or I do 1D DP, it would be O of n inside the loop. I tried to, say like, okay, let's try to do dynamic programming, where I say like, okay, up to an index I is either, the optimal solution up to, but not necessarily ending at index I, and another one where it's like, okay, I must force every solution to end at index I, so that way it's like, when I want the optimal solution, I loop through the best solution at every index I and get the best one out of those, and so on. Everything that I tried with dynamic programming ended up always being too slow. And then with sliding window, it ended up being like always incorrect. Inside of the editorial, they showed this minimum size subarray sum problem that I ended up solving. So the very first time that I solved this, I did it with a sliding window approach. So if I look at my solutions here, like my very first one, just typical sliding window, just keep incrementing and decrementing and so on, making it nice and easy, which I cannot do for this problem because again, the nice part of sliding window is that like, well, in the context of this problem is that like, the numbers are all positive. When they're negative, it kind of messes up with your results. And one of the follow-ups to this problem was like, hey, can you also do it in n log n, right? And I did come up with a way to do this problem in n log n, but I got screwed over by the fact that some numbers are negative. Then when I realized, okay, in this problem the numbers are positive, I was able to do it in O of n log n time, which is essentially I do my dynamic programming idea where I say, hey, at index I will find the best solution. So DP will take in a number. So this will be an index, and index I will give me the best result that ends at index I, right? And so at index I need to find, the tightest leftmost index that will work to make this subarray sum at least greater or equal to k. So I get all the prefix sums. So one of the very first things that I did inside the other problem is like, okay, if I get all the prefix sums, right, it's like from 0, it's just the first element. For at x1, it's like the sum of the first two elements and so on, build up that array. Then once I have that prefix sum array, then I can get the subarray sum between any two indices I and j in O of 1 time, right? I just do prefix sums of j minus prefix sums of I minus 1, right? Because again, like, prefix sums of I is equal to, the sum between every element from 0 to I, which is equal to, so if I want the sum from I to j, I can take the sum, prefix sum of everything up to j, so 0 to j, minus everything from 0 to I minus 1, right? And that way I'll get the sum of everything from I to j. So therefore, it's like once I have that prefix sum array built up, I can get the sum of a subarray between indices I and j in just O of 1 time, right? And so then what I did is like, okay, using that idea, it's like, okay, if I have an index I, then essentially, since I only have positive numbers, the bigger that I make my array, the bigger my sum will be, right? The smaller that I make it, the smaller my sum will be. So if I look at the very first thing, and that happens to be, like large enough, I'm like, okay, at some point when I make my pointer too small, it might be the case that the subarray sum is not large enough, right? I need it to be greater or equal to k, greater or equal to target. So it's like, okay, it'll be true, and then at some point it might become false, right? It's no longer greater or equal to k or greater or equal to target. So essentially, if you think of it as an array of sorted booleans, essentially a bunch of trues followed by a bunch of falses, and you want to find that rightmost true index, right? Because that rightmost true index represents, the largest index, such that between that index and index I, the subarray sum is greater or equal to k, right? And if I just shifted this by one more, then it would no longer be greater or equal to k or target, right? So essentially, I'm able to binary search for that left index. So that's like, okay, for this index I, the optimal solution will come from this index over here, because again, no numbers are negative, right? So essentially, instead of each DP call, I do log n work, and there's up to n DP calls. So the overall time complexity is O of n log n, which I was able to do and solve this problem. But again, for this problem, the tricky part is that the numbers are negative, and so I ended up giving up per se, because I saw there were no hints and I got really stuck. So I started reading the editorial, and then inside of the editorial I found this priority queue solution. And then I started reading, and I thought like, oh my goodness, I understand what I need to do, because one thing that I realized is like, okay, if I don't want to make this from n squared to O of n, I was like, I have to do some kind of two-pointer or sliding window approach. And I tried a lot of greedy ideas with two pointers that every single one of them did not work. And then with this, I figured like, okay, with sliding window, somehow I need to be able to make a decision. And one thing that was really tearing me apart is that a problem like this, for example, this subarray, so if the sum of these elements is equal to 167, right? So I was trying to really tell myself, like, okay, in an example like this, how do I know whether I want to put my left pointer here or keep it here, right? If k is equal to 168, in this case, I would need to keep my left index here, right? Because the point is that, like, this subarray sum, 84 minus 37, is a positive integer, but you're paying an extra cost of length 2 for the subarray, right? So it's like, do I keep my index L here or do I not? Well, if k was equal to 168, it would require you to keep every element, right? So like here, k7, it's like k is equal to 168, you need all 5 elements. But otherwise, if it's equal to 167, then you just need these 3, right? So like case 4 is like k is equal to 167, I only need 3 numbers. So it's like somehow dependent on k, I need to know whether I shift the left and right pointer, but then again, if I do that for every right pointer, it becomes n squared. So I was like, how do I make the decision point, right? And this is why I'm saying that inside of here, where is it? That I really like Noah's comment, because this is essentially the game-changing comment. The insight that you can discard each prefix sum after finding the first index that creates the window with sum greater or equal to k is freaking game-changing. It's so obvious in a way, yet so impactful on time complexity. Absolutely. So one thing I realized is that somehow, some way, I need a way to make decisions and commit to them and never look back. But I really struggled on how to do that. And so what I figured out from the editorial, which also Noah here figured out, is that, hey, if I take, you know, every single index inside of the array, and I take the prefix sum, I can use that as a starting point, right? And so I can essentially build from the left of my array here, open up, and then it's like, okay, if I have a solution here with a previous index over here, I can just utilize that, bada bing, and never look back again, right? Because again, I'm opening it from the beginning, and then once I go over onwards and on and on and on, any solution that ends over here with the same one will only result in a bigger array, so I can ignore them. So if I find a solution here that works, then I can essentially scrap it forever. And the trick is, again, to populate them as you go and do a running sum. Because again, you only want to consider, you know, solutions that are smaller than you, so that you might as well do things that way. And yeah, and a heap is perfect, because if you look at the smallest prefix sum, again, the way that you get the subarray between two indices is that, like, you subtract by the left indices, you know, prefix sum -1 or 0 if it's I is equal to 0 here. And so it's like you're essentially trying to minimize that value. So, like, you know, a heap was kind of like perfect in that sense, where it's like, oh, you want to minimize this value to make the sum as great as possible, then you might as well use the min heap, and then, you know, keep popping from the min heap as long as you keep finding valid solutions and kind of go on your way there. But I don't think I'm, like, you know, going to be the best explainer for this one, because again, the editorial did a pretty perfect, fantastic job explaining this. But yeah, that's how I was able to solve it in the end. It's like I knew that I needed a way to commit to decisions. I could not figure it out on my own. I ended up having to look at the editorial. It was definitely a fun challenge solving this, both with the setting window and my dynamic programming idea, which the dynamic programming idea seems to not even be in here. So maybe I could have explained that a little better, because that is a pretty cool solution, I won't lie. Yeah, so honestly, this problem gave me a lot of insight, a lot of valuable wisdom and learnings. But yeah, one thing I will say is I'm definitely glad to just be done with it. I do not mind that I got 5.4% solution. I learned a lot. I took away a lot. Noah's comment, could not agree with you more. It is absolutely game-changing. That is definitely a pattern that I want to recognize more often, right? Where it's like, I know I must make a decision, I don't know how, and here's a way how, right? Where it's like, oh yeah, you might end up not doing constant time work. One call you might end up doing O of n work, but across all the n calls altogether, you only do an extra O of n work. Therefore, it's all like O of n, blah blah blah. Like that kind of pattern is it comes up a lot, and we've seen that pattern before on this channel on the Daily LeetCode challenges. But yeah, again, this was a pretty tricky, tough problem. You had to realize a lot of things to get to the solution to the problem, and even so, I had to look at the editorial to get, like, you know, that extra boost to the end, because there were no hints for this problem. So yeah, so definitely a tricky problem. So let me know how you guys did in the comment section down below if you also did this problem. But yeah, this one definitely got the better of me in one way or another. But otherwise, that is pretty much it for this video. If you did find it useful or enjoyable or educational in any way, shape, or form, I'd highly appreciate if you left a like or a comment. Otherwise, I'll catch you in the next one. So until then, ciao, my friend. Bye-bye.